in order for a vector to be parallel to another vector, it has to go in the same direction. It doesn't matter if one is short and one is long. They would still be parallel to each other. Even if it was going in the opposite direction, it would still be parallel to it. So if we want to find a vector parallel to 4, -3, we just need to find something that goes in the same direction. So any multiple of this, for example, you could choose 2, (8, -6) would be parallel. We could also use a fraction. What is special about this one that I just chose? 1/5 for -3. Okay, we'll put it up in a second. Okay, so we can graph them in 3D on this calculator. There it is. Oh, it's getting too bright. It's going. Oh, gone. Okay, try that again. Here we go. There it is. Oh, snap a picture. The one vector is here, and the other vector is here. And if you rotate it right in your mind, they look like they're 90 degrees. You can rotate it on there with the touchpad. Nice. All right. Back to our question. Something that's not parallel. So basically, did anybody figure out what was special about the one that I wrote up here? The 1/5 for -3? Just because I like the number 5? It is the unit vector. That one would have a length of 1. So basically, any number that goes in any multiple of 4, -3 would make it parallel. And sometimes when we think of our direction vector as 4 and -3, well, 4 is basically your x, right? That's basically your run. Your -3 is your y. That's basically your rise. And what we learned about parallel lines was their slopes had to be the same. So in this one, your ratio of your run to your rise, or your rise to your run, would have to be the same as well. So it's the same idea as slopes. So if we wanted something not parallel to you, just have to change one of the numbers. 8, -3, that would be a different slope, and that would not be parallel. Orthogonal or perpendicular. What did we do with slopes when we wanted perpendicular? We made it negative and flipped them, right? Negative reciprocal. So if this had 4 and -3, I could now have 3 and 4. And we could check it by doing the dot product. And you get 12 minus 12, which is 0. And that shows that they're orthogonal or perpendicular as well. Of course, any multiple of this would work. So if you did 6 and 8, or 12 and 16, those would all work as well. So we've got one vector w here, 1 and negative 3. The other vector v has 2 and x. What does x have to be if they're parallel? Negative 6. So what you noticed was that in order to get a 2 here, I'd have to multiply this vector by 2, and then there would be a negative 6 there. And then those vectors would be in the same direction. So if you're figuring out something is parallel, you're just putting a number out in front. If you wanted to solve this one algebraically, say, I don't know what the number is out in front. Because I can make this question a lot harder, right? I can make this 1.372. And then it would not be quite as easy. Well, that one's not hard. 1.4 here, and then 1.372. So we can't do some simple mental math to figure it out. Then what you could do is just put a k out in front. And this would tell us that k times 1 has to equal 2. I wonder what k is. And then you figure, oh, k is 2, and then you go 2 times negative 3 and get negative 6. Of course, with these numbers, you'd have 1.4 times by k has to equal 1.372. It's not going to be a very nice number. And then once you figure that out, you can multiply the negative 3 by that 0.9 to figure out what x is. So that's an algebraic way that you could think about this if the numbers weren't easy. But for this one, with our original numbers here of 1 and 2, it was really quite easy to see that it was just doubled. And we could figure it out that way. For perpendicular, what strategy could you use to find out if they're perpendicular? We could use the scalar product or the dot product. Which would tell us that 2 minus 3x had to equal 0. And so 2 equals 3x, and x equals 2/3.